So this is going to be a lecture video on chapter 11 where we're going to continue to talk about rotation. So the first topic that we want to look at is torque, and torque is the rotational equivalent of force. And the Greek letter that we're going to use is tau. And in order to find torque, we're going to take force times radius. So let's think about a door. And let's say we have some hinges over here. And then we usually put our handles clear out here. So the force that we would be exerting would be here at the handle. And the lever arm distance is the distance from the force to the pivot point. So my distance, that radius that we're going to be using, would be that distance to the pivot point. And we usually put the door handle clear out here because if we have a bigger radius, that allows for a larger amount of torque. The other thing we want to think about is when we apply that force, typically we are applying that force at an angle to the door, perpendicular to the door. So I would be pushing into the door, and this is the plane of the door. So I'm going to be perpendicular to the plane of that door. So when we talked about forces before and we talked about work, we said that it was important that we looked at the angle. So it's going to be the same thing for torque, and to have the maximum amount of torque, I want to be perpendicular. If I'm at any other angle, then I want to use the sine of that angle. Whereas for work, we were using cosine. Here we're going to be using sine of that angle. And the units that we're going to use for torque are Newton meters. The direction on torque is going to be the same as our rotational velocity. If it's clockwise, it's going to be negative, and if it's counterclockwise, it's going to be positive. So we have a torque problem here. So I am using a gardening tool. I'm exerting a force here that's perpendicular to the bar. So there's the force of the hand. And then there's going to be some resistance here by the weed. And the weed, as I push down over here, it's going to force the weed up, and there's going to be some resistance from this weed. So if 1.323 Newton meters of torque is required to pull the weed, then what force did the weed exert on the tool? So I need to use the radius from the pivot point here to the weed because it's asking me for the force that the weed exerted. So the torque is equal to the force times the radius. Just rearrange the equations solving for force and take torque divided by the radius. So here's the torque that I was given, there's the radius in meters, and that gets me a force of 31 newtons. Okay, according to Newton's second law, F equals ma, and I'm just going to rearrange and put this in rotational terms. So for force, I'm going to use torque. For mass, we're going to use rotational inertia. And for acceleration, we're going to use alpha, which is our angular acceleration. So that's another way that we could find torque. So here's an equation that I could use that uses angular acceleration. So we have a CD. It's going from rest to 450 revolutions per minute in 3 revolutions. And if it has a radius of 6 centimeters and a mass of 17, what is the torque exerted on it? So the first thing I'm going to do is use one of my 3 motion equations that we have outfitted in terms of angular quantities. So my final is going to be 450, and I have to change the revolutions per minute into meters per second. So I multiply by 2 pi and divide by 60. My initial is from rest, so it's 0. And then the 3 revolutions, I have to change that into radians. So I took 3 times 2 pi. And I got 59 radians per second squared for my angular acceleration. Next thing I have to do is find my rotational inertia. So I do 1/2 mr squared. So 1/2 the mass, which is in kilograms, and the radius up here, centimeters into meters, and I should get 3.1 times 10 to the negative fifth kilogram meter squared. So then finally, my torque is equal to my rotational inertia times my angular acceleration. So this is the rotational inertia I found above, and the angular acceleration, and I should get 0.0018 Newton meters for my torque. So when we talked about Newton's first law, we said that an object in motion stays in motion, an object at rest stays at rest, unless there's an unbalanced force acting on an object. So the same thing is true for rotating objects. So an object is rotating, then that means it's going to keep rotating in the same direction at the same speed unless there is an unbalanced torque that acts on it. So if we won't want it to change at all, then we say it's at equilibrium, and that means that the net torque is 0. So in this case, we can see we have a plank. So there's a force exerted up by this man, so that means there's an upward torque. Here we have another torque exerted by the woman, and then we have a downward torque from this child, his weight. And those two upward torques have to be able to balance the downward torque in order for this thing to stay at equilibrium. And when we talk a lot about torques, we talk about the center of mass. And the center of mass is where we're going to say that all of the mass is said to be located. And if an object is going to be balanced, it must be supported over the center of mass. So if we had this particular scenario, if this is going to stay balanced, then that means it has to be supported at the center of mass. So that means this would be my center of mass because that's where it's being supported. Okay, here we have an equilibrium problem. All right, so we are going to have a point of pivot, and my pivot point is going to be located right here. Then we have the upper body that's exerting a force. We also have the lower body that is exerting a force. Okay, this one's going to make it rotate one way if it was allowed to rotate. This force or torque is going to be rotating the other way. So these two have to be balanced in order for this to be stable. So it gives me all the information over here. So the torque of the upper body has to be balanced and be the same as the torque from the lower body. So torque is force times radius for the upper body, force times radius for the lower body. They're asking me to find the force produced by the upper body, and the radius would be the distance from where the center of mass is of the lower body to the pivot point, and they tell me that's a distance of 39 centimeters. Nope, sorry, the upward body is 28 centimeters, so 0.28 in meters. The lower body has a mass of 54 times 9.81 is going to give me the force, and then that distance is 0.39. So I think I messed up before. So the lower body to here, that is the 0.39, and for the upper body to the pivot point is going to be the 0.28. So those are in the correct spot, and we get a force of 740 newtons. In the problem that you're going to see on your assignment, it's going to be similar to that. I think you have like a teeter-totter, and we have a child that's sitting on one end. That'll be my child. And then I'm going to have a parent push over here, and that means those two torques have to be the same. So I would know the force and the radius to this side, and then the force and the radius to the pivot point here. And those two would have to be balanced. All right, we talked about angular momentum before. Angular momentum is inertia times the angular velocity. And the SI unit that we're going to use is kilogram meters squared per second. If we have a particle, you will be using this later. I believe in your assignment we're talking about somebody on a piano bench and you're throwing something at them, a weight, I believe. I think you're also going to have one on your worksheet about it where we have a merry-go-round and then we have a person that's running to jump on the merry-go-round. and that person's velocity, they give you the linear velocity. So that's when we would be using that. All right, we already talked about conservation of angular momentum in class, and we said that angular momentum, just like linear momentum, is conserved. So that means if I change either the mass or the radius, that means I'm changing the moment of inertia, and that means that my angular velocity would have to change in order to end up with the same amount of angular momentum. So in this case, the man has a bigger radius because his arms are out. When he brings the arms in, the radius decreases, which means that the angular velocity would increase. This is a setup that's similar to what we're going to be doing in the lab, where we are going to have a disc that's rotating, and then we're going to drop another disc on top of it. And since the mass increases, then the angular velocity would slow down. Now the example problem we're going to do is we are going to have a turntable, and on that turntable we're going to have a mouse, and the mouse is sitting right out here on the edge. And as this happens, the mouse is going to start to move to the center, and they want me to find the angular velocity when the mouse is at the center. So we're going to conserve angular momentum. So the initial angular momentum has to be equal to the final angular momentum. This is going to be the rotational inertia times the angular velocity of the turntable, the turntable. This is going to be the mouse. And then later I have the rotational inertia of the turntable plus the mouse, and then I'm trying to find the angular velocity at the end. So they gave me the rotational inertia of the turntable, and they gave me the angular velocity, which is here. I have a mouse, and this will need to be in kilograms, and I'm trying to find I. So for I for my mouse, it's going to be kind of like a hoop going around the outside. So I'm going to use mr squared. So m times the radius, which is how far he is from the center, squared, times the initial angular velocity, which is 3.5. Now later, I have the I have the rotational inertia of the turntable, and then the mouse now is in the middle. So he doesn't have any radius, so his rotational inertia is now 0. And I'm trying to find the final angular velocity. When I did that, I got 4.0 radians per second, which means that as the mouse moved in and the mass was near the center, so this is like bringing your arms in, or the ice skater bringing her arms in, as the radius shrunk because the mass moved toward the center, then it has to speed up. Next, we're going to talk about work and power in terms of angular or rotational quantities. So work is going to be equal to, we had it before in linear terms as force times distance. And for force, we said now that force is torque in the rotational world. And change in my angle, my radians, is my distance in the rotational world. And if we want to find power, power is work divided by time. And for work, we said we could take torque times my angle. And then if we divide by time, we get my power. We also did have an alternative one that we used for linear power, and that was force times velocity. So if I put that in rotational quantities, force we said is torque, linear velocity would become angular velocity. So now we have an example problem using work and power. So for a home repair, we have to turn the handle of a screwdriver 27 times. If I apply an average force of 13 newtons tangentially, that's that 90 degrees, to the 3 centimeter diameter handle, how much work have I done? And if I do this in 24 seconds, what is the power? So torque is force times radius. I'm at 90 degrees, so this is going to be 1. And they gave me my diameter, so I'm going to use half the diameter to find the radius. And then I'm going to multiply by my force. So that's going to get me my torque. So for work, I'm going to take torque times my radians. So in order to find, there's my torque. My radians is going to be 27 times, or 27 rotations, and I have to change that into radians, so I multiply by 2 pi to get 33 joules of work. And then to find my power, I take work divided by time, so 33 divided by my time at 24, and that gets me 1.4 watts. And lastly, we talked already about the right-hand rule. And if you curve your fingers in the direction of the motion, that's going to tell you the direction of your angular velocity. And that's it for chapter 11.